Establishing cell towers and landing pads on the moon is just a temporary science project. True survival on another planet demands something much more brutal. It requires a complete paradigm shift. It requires entirely severing the logistical umbilical cord to the planet Earth. Welcome to Phase 3. In our last video, we executed a clinical dissection of Phase 2, the heavy infrastructure deployment and the creation of a localized municipal power grid. But that was just the warm-up. The operational timeline has now shifted into an aggressive, closed-loop industrial matrix. This phase starts in 2032, logs through 2036 and casts a shadow all the way to 2070. Look at the raw data matrix delivered by Carlos Garcia Gallan's master roadmap. The mandate outlines an uncompromising logistical surge. Exactly 29 heavy lift launches. They are delivering a colossal 150,000 kg payload matrix directly onto the lunar south pole. Why is NASA dropping that specific amount of weight? Because that is exactly what it takes to build full-scale nuclear power plants, multi-room automated habitation networks, and heavy material refineries on an alien world. Now, you might be thinking this is just a futuristic science fiction fantasy. It is not. This is a cold, calculated engineering roadmap designed to seize resource dominance before international competitors freeze them out of the primary strategic corridors. To prove exactly how this will happen, we didn't just look at the concept art. We audited the foundational physics of the rocket equation, analyzed the thermodynamics of regolith sintering, and broke down the closed-loop life support architectures. This is the final realization of human permanence. How do you build an independent economy in deep space if you have to drag every single drop of water and every steel beam out of Earth's massive gravity well? You don't. You live off the land. To comprehend the absolute necessity of Phase 3, we must audit the foundational physics barrier that has choked space exploration since the dawn of the Apollo era. The absolute tyranny of the rocket equation. For over 60 years, every space mission has operated under a crushing economic math tax. To keep a single human alive in deep space, space programs must launch millions of pounds of explosive fuel just to push a tiny fraction of breathable air, water, and structural shielding out of Earth's atmosphere. True permanence requires the complete implementation of in-situ resource utilization. In simple terms, you have to harvest the local dirt. If a geopolitical faction fails to automate the harvesting of local resources, their operational footprint remains entirely vulnerable. One budget cut, one political shift, or one launch failure at home, and the astronauts starve. Phase 3 solves this systematic vulnerability by converting raw lunar dirt into strategic commodities. Refined oxygen, hydrogen, water, and rare earth elements. To make this transition, the transportation engine must scale up violently. The architecture demands an immediate transition to maximum class commercial landers. These heavy lift configurations must push individual touchdown capacities to an unyielding 8 metric ton structural ceiling. Look at the numbers. They are dropping 150,000 kg in total. That is roughly the weight of a fully loaded commercial Boeing 747 aircraft, systematically disassembled and dropped onto the South Pole. This massive payload volume allows the delivery of full-scale industrial machinery, integrated habitat nodes, and deep crater resource extraction rigs directly to the surface. Simultaneously, the program initiates a large cargo return framework, establishing an automated logistical loop capable of launching 500 kilograms of refined, high-value materials back to Earth on every trip. This heavy landing infrastructure operates exactly like an autonomous planetary freight train. It slams onto a frictionless runway, dropping off completely off-grid factories without a single human coordinator required on site. You can land the factory, but you cannot afford to ship heavy concrete or steel beams across cislunar space to build the walls. So, how do you construct blast shields and roads on a planet with no trees and no steel mills? You weaponize the dirt itself. The Phase 3 architecture deploys automated robotic assets specifically designed to convert raw regolith into durable, sustainable infrastructure. You would expect a lunar factory to rely on soft terrestrial materials brought from home. But the reality is that the program utilizes the highly abrasive, microscopic, glass-like particles of the lunar soil as its primary building block. The main construction techniques rely on a combination of autonomous corbelling, 3D printing, and high-energy microwave sintering. We need to understand exactly what sintering is. Sintering regolith is identical to using a high-energy laser to weld loose, razor-sharp volcanic dust into solid ballistic armor. The robots do not mix cement. They use intense, focused heat to melt the atomic structure of the moon dust, fusing it together into thick, unbreakable bricks and smooth landing pads. This automated construction cycle operates continuously in the dead silence of space. These robotic masons build massive blast walls around the landing zones to protect against rocket exhaust. They line the internal tunnel networks, they seal the permanent structural enclosures, and they do all this entirely alone. By the time human crews actually arrive for their long duration shifts, the robots have already transformed millions of loose atomic daggers into impenetrable defensive shields capable of absorbing extreme radiation and micrometeorite impacts. But laser melting dirt and refining rocket fuel out of frozen ice takes a terrifying amount of electricity. How do you power a heavy industrial factory through a 2-week-long cryogenic night? You cannot rely on the sun. To continuously power an expanding industrial matrix, the facility must scale up to a permanent, non-intermittent power source. Phase 3 marks the official deployment of full-scale fission surface power reactors. These are compact, highly advanced nuclear units that operate completely independent of local solar illumination. They deliver a steady, multi-megawatt base load to the entire lunar grid. This nuclear infrastructure is a non-negotiable prerequisite. Extracting oxygen and hydrogen from frozen regolith demands an immense, uninterrupted thermal and electrical input. Solar panels simply cannot provide this during the devastating 354-hour lunar night. The reactor designs utilize highly enriched, rugged, solid fuel cores paired with advanced heat pipes to silently bleed off excess heat into the vacuum of space. Now, you might ask, how does a nuclear system survive decades in a highly toxic environment without human maintenance? The answer lies in eliminating moving parts. There are no spinning turbines to break down. The core generator loop relies entirely on static thermoelectric conversion modules, utilizing the extreme temperature differences to drive electrical currents straight into the grid. Think of a fission surface reactor as an artificial atomic sun. It is buried safely under meters of dense alien soil, shielding the surface from radiation. Yet, it feeds a massive, steady current of electricity to distant outposts, completely unbothered by the fact that the local terrain is locked in a cryogenic dark phase. If the state apparatus cannot transition the base to atomic power, the base remains a consumption model. With nuclear fission, it becomes a relentless, unstoppable production engine. You have the rockets, you have the printed blast walls, you have the nuclear power grids. But none of that matters if the human lungs inside the base are starved of oxygen. How do you breathe in a permanent vacuum? The star of the Phase 3 show is the delivery of the first permanent lunar surface habitats. Look at the technical constraints. These structures are not small tin cans. They expand into massive multi-room complexes exceeding 100 cubic meters of internal pressurized volume, roughly the interior size of a standard semi-truck trailer spread across multiple strategic locations. But putting a metal box on the moon is easy. Keeping people alive inside it is the ultimate engineering nightmare. Apparently, human lungs remain stubbornly uncooperative when presented with an absolute vacuum, making environmental containment an irritatingly strict requirement. Each module is integrated with an advanced environmental control and life support system, or ECLSS. The internal chemical engineering loops of the ECLSS must actively reclaim, purify, and recycle exactly 98% of all atmospheric gases and wastewater. Every drop of sweat, every exhale of carbon dioxide is captured, chemically scrubbed, and returned as fresh water and breathable air. The ECLSS habitat functions as a synthetic, hyper-engineered mechanical lung. It wrestles with the crushing void of a vacuum to continuously recycle every single breath of human air and every microscopic drop of metabolic moisture. By marrying this closed-loop life support system with the local oxygen extraction plants running on nuclear power, the base permanently purges the risk of atmospheric starvation, cementing true human permanence on the absolute edge of the frontier. As we calculate our forward strategic trajectory from our current baseline year of 2026, the evolution of the moon base moves from a high-stakes engineering blueprint into an unyielding geopolitical reality. In 2032, Phase 3 deploys the first megawatt fission reactors. By 2034, the heavy cargo landers drop the primary habitat modules, projecting out towards the macro-industrial horizon of 2070. This Phase 3 architecture completely transforms the economics of deep space. The moon base is no longer a heavily subsidized science project. It is an independent, self-sustaining industrial launchpad for deep space transit to Mars and beyond. Factions that master local resource extraction during this window will permanently control the primary commodities of the next century, including refined hydrogen propellant and the rare helium-3 isotopes required for next-generation fusion grids. You would expect governments to dictate resource distribution, but the reality is that the sovereign entities and commercial syndicates that physically control these automated refineries will entirely dictate the terms of deep space commerce for the next 50 years. Factions chained to Earth's supply lines will be systematically starved out, outpaced, and left behind in the dirt. Space exploration is now a high-velocity industrial race to achieve absolute resource independence. Now, look at the structural trade-offs of this autonomous layout. Do you believe that achieving complete independence from Earth's supply lines secures national sovereignty? Or does the rise of autonomous private resource extraction plants on the lunar surface generate a dangerous corporate legal singularity that completely strips sovereign states of their ability to govern cislunar space? Leave your detailed analytical perspective in the comment section below. We will meet in our next video. Until then, stay analytical and stay curious.